Hi, I'm Cliff Elgin. I am lead researcher here at Ordinal Research Institute. Ordinal Research Institute is a nonprofit organization headquartered in Pasadena, California. We are an independent research community. Our mission is to explore groundbreaking ideas by collaborating with physicists around the world. Our research includes embedded spacetime manifolds, which is closely related to today's talk by Dr. Matej Pavšič from the Jožef Stefan Institute in Slovenia. Thank you, Dr. Pavšič.
Okay, thank you for this introduction. Now, the question is here. I have this meeting is being recorded by the host or participant. Then how to get rid of this message?
I think there's a little button that says "Got it." It's probably blue.
Yes, I did it, but nothing happened. Okay, maybe I did not press enough. Okay, thank you. So this talk today is entitled Branes and Quantized Fields, with a subtitle Towards Quantum Gravity Within Braneworld Scenarios. So first, I will talk about brane as a point in a brane space, which is an infinite dimensional space with a metric in general. In general, this metric, this space is curved. But in particular, it can be flat. In that case, the talk is about a flat brane space in which a brane is a bunch of non-interacting particles. It is just like a bunch of non-interacting point particles, more precisely, their word lines. So this bunch of word lines. First, I will consider classical case, and then I will consider quantized fields. If we introduce interactions between the fields, then for a particular interaction, we obtain classical Nambu-Goto brane as an expectation value. At the end, I will touch on the role of configuration space in physics in general, not only in quantum theory, where configuration space is quite ubiquitous, but also in classical physics is very important. In fact, it is the basic space. Okay, let me now try to go on. So, introduction. Relativistic membranes of arbitrary dimension, usually called branes, are very important objects in theoretical physics. Attractive possibility is the Braneworld scenario, according to which our world is a brane in a four-dimensional space, in higher dimensional space. So a four-dimensional membrane in higher dimensional space. So here are examples of two such possible branes. Especially interesting is this possibility that the brane self-intersects. And on this self-intersection, behaves as a word line of classical particle. So quantization of gravity could be achieved by quantizing the brane. Unfortunately, quantization of the Dirac-Nambu-Goto brane, this is the usual minimal surface brane, is a tau problem, not solved in general. I will show how to solve this problem by considering the brane as a point in an infinite dimensional brane space M that in general can be curved. And there are particular cases of the metric in M space. One metric gives you the Dirac-Nambu-Goto brane. This is the usual minimal surface brane. The other possibility is flat brane. Then a brane is like a bunch of point particle word lines. Okay, so let me try. Yeah, so this is a bunch of straight word lines. Word lines are straight. And a brane is a continuous unit, and that is a bunch, yeah. And quantization of a flat brane leads to a system of non-interacting quantum fields, phi of R. R is the index which denotes which field. There are many fields. If we consider interactions among the quantized field, for instance, these are coupling constant, this lambda RS couples two different fields, then the effective classical theory gives a brane living in a curved space, which in particular can be the Dirac-Nambu-Goto base. So this interaction among fields leads in the classical theory as an effective theory to all sorts of branes, classical branes, and one of those branes is just the usual Dirac-Nambu-Goto brane. Okay, I will talk now about brane as a point in the brane space. The Dirac-Nambu-Goto brane action is given by this expression here. This is the minimal surface action in which there is, of course, integration over the parameters psi of the surface and multiplied by the determinant gamma of the induced metric on the brane. Here, x nu of psi are embedding functions of the brane. So index mu runs over the embedding space-time coordinates, and index a runs over the over the coordinates or parameters of the brane's worksheet. Now, interesting thing is, look, an equivalent action is the so-called shield action, in which there is no square root. Because there is no square root, this action is not reparameterization invariant. This action is reparameterization invariant, but this action is not. And consequence of the equation of motion derived from this action is that determinant of the induced metric is constant, k, kappa, k. And the choice of this k determines a gauge, that is reparameterization of the brane. Additionally, we can choose gauge in such a way that the determinant factorizes into these two terms, where gamma bar is the determinant in the space of brane's parameters, whereas A are parameters on the worksheet. So you have here additional parameter in the time-like direction. And this x dot square is derivative of brane coordinates with respect to time-like coordinates, tau. So x dot is this partial derivative with respect to tau. So this action, this choice of gauge becomes this action. And this form of the action is shield action, yes. And now we can rewrite this action so to insert a delta function. Of course, then you have here two integration, not only one, but it is by doing so, you can write this action then in this way, namely you proclaim this object here as a metric, and this expression here can be written in this way with the metric rho mu of sigma. So these are velocities, generalized velocities, velocities of the point in brane space, and this is the metric. Now at this point, it is very convenient to introduce a shorthand notation so that you promote this sigma here as index. And this x dot of mu sigma is velocity, where mu is discrete part of the index, mu goes over discrete embedding space time coordinates, and sigma is a continuous index denoting the point on the brane. So in this way, we arrive at the coordinates. And we also write the metric in this way. So this expression here is then written in this way, which is just extension of the usual 10 notation from finite dimensions to infinite dimensions. Now, this object under integral is the quadratic form in an infinite dimensional space. It is invariant under diffeomorphism in the brane space, that is under coordinate transformations in the brane space, that is under transformations of the brane's coordinates x mu of sigma. This mu of sigma does not mean that mu is function. This bracket just reminds us that the index is continuous, nothing else. So each x mu represents a kinematically possible brane. And a curve in M is given by tau-dependent functions. So this is tau. This is a parameter which traces the word line in the brane space. So this x dot is velocity of a point in M. So we can rewrite this action. So this by doing some manipulations which are not so essential for the moment, you can look at the papers. So that instead of this kappa and k, we have kappa tilde and k tilde, where kappa tilde is the integral of this kappa, and k is also the integral. And this is the shield action for point particle in infinite dimensional space. This is a generalization to infinite dimensions of the shield action for the relativistic point particle in curved space-time with the metric G mu nu. The later action, so this action here, is a gauge fixed action for a relativistic point particle, which is described by the reparameterization invariant action. So this is the usual action for relativistic point particles. And we see that in brane space, we have something quite analogous. So we have this action here. Yeah. So instead of this action here, okay, this k is analogous to mass. Here we have mass over k, but then a relativistic point particle action is just this mass without this k. And so we have also here just k tilde, which is analogous to mass in infinite dimensional brane space. Now, what is interesting is that we can derive the equation of motion. The equation of motion by performing functional derivatives with respect to these coordinates here. A functional derivative is usually denoted with this delta over delta x as function of sigma, but in our notation, I can just write a partial with respect to partial x of the sigma, because functional derivative is is like partial derivative in infinite dimension. And so I denote it by this usual symbol for partial derivative. By distinguishing up and down indexes, which are raised or lowered by the metric or its inverse, and introducing Christoforol symbols in base space, we arrive at this equation here, which has the same form as the well-known geodetic equation in finite dimension. So this is geodetic equation in brane space. So how we derive it? In the usual notation, we just have the action as a function. Lagrangian is function of velocities and coordinates, and variation gives this variation for this action here gives the geodetic equation in M, which is this one here. Now, this is important. This equation here is valid for any metric rho. And okay. For any metric. In particular, the metric can be this one. Then the action becomes obtains this is this one, and variation of the later action gives this equation here, which is the well-known equation of the usual Dirac-Nambu-Goto brane. The same equation of motion can be derived also from this action for the Dirac-Nambu-Goto brane, in which we take the gauge such that determinant splits into these two parts. Sorry if this is complicated. Essentially, that we are doing just something that we are doing in finite dimension, geodetic equation. Okay. Okay. Now, a particular choice of metric is flat metric. Flat metric, which is extension of Minkowski metric to infinite dimension. Minkowski metric is diagonal, and this delta function, okay, this sigma is more dimensional. It's not just one dimensional. Implicit index A is hidden here. So this is also diagonal, like Minkowski metric, but now diagonal in infinite dimensional space. Then the action obtains this simple form here. Just eta mu and this, and variation of this action gives you this equation of motion here. And we can choose a gauge in which this x tilde square is equal 1. And so we obtain just the second order equation for the variables x tau of sigma with solution which is given here, where v of sigma is velocity, which can be arbitrary, and x, okay, yeah, it's initial velocity, yeah, and this x of sigma is initial position. So this is a bunch of straightforward lines. In other words, this equation represents a continuum limit of a system of non-interacting point particle tracing straightforward lines. Look, here are examples of such systems. So the metric, as I told you, is simple one, extension of Minkowski's metric, which gives flat word lines. And now if you see, all word lines are flat. Word lines are this. The structure of the object is very complicated, interesting, with this self-interaction or in this way. But all word lines are straight. So instead of this metric, we can consider this metric. This is no longer a flat brane space, it is curved. And the word lines are no longer flat. So we have this interesting self-intersecting structures. So these plots are calculated by Mathematica. Now, if we take this metric, square root of gamma bar times this, and if we take care of boundary condition such that the brane does not, or the string in this case, does not self-intersect, then we get a worksheet of the Dirac-Nambu-Goto string, the usual string of string theory. So here are two possible cases. So the string is this one here, but if string moves, it sweeps or traces worksheet. Either this or here is, in fact, the string is rotating. String is this, and so the usual Nambu-Goto string is within this model particular case for a particular choice of metric. But the idea here is that the metric should not be put ad hoc. Like in Einstein theory, the metric is envisaged here as being dynamical, as solution of certain dynamical equations of motion, and that you have various possibilities, various possible brane theories or string theories. Okay, let us go on. So, quantization of the system described by the action for the flat brane can be performed in analogous way as the quantization of the point particle in space-time. The action implies the constraint between the canonical momenta, where this quadratic form is explicitly integration over canonical momenta of the brane. And upon quantization, the constraint becomes the generalized Klein-Gordon equation. So this is this equation here, where P hat are now operators, functional derivatives with respect to the embedding functions. The field phi is a functional of the Brane's embedding function, and momenta are functional derivatives. Like in the usual quantum theory, momenta are partial derivatives with respect to coordinates. Okay, the corresponding action for the generalized Klein-Gordon equation is this one here. So this is the action. This is just like the well-known Klein-Gordon equation. In this notation, you just see straightforward that this is generalized to infinite dimensions. So if you perform variation, then you get this equation here, which in the usual notation has this form here. So functional of embedding function, and here this operator in which you have doubled functional derivative and this. Now, if this generalized Klein-Gordon field is just the product of these fields, then by using these identifications, in which M is the segment, mass of a brane segment delta sigma, and the functional derivative is multiplied by mass by the brane, the segment delta sigma of the brane is the usual partial derivative, and so this equation becomes the system of equations for those fields. So there are many fields. This phi of sigma 0, zero is the point at which this field is taken. So in this setup, the segment of the brane around chosen point sigma 0 behaves as a point particle and satisfies the point particle Klein-Gordon equation. Okay, this was a continuous case, but in the following, just to illustrate the ideas, I will describe the flat brane by means of many particle non-interacting field theory. Different segments of the brane behave as distinguishable point particles, each being described by a different scalar field. The action for a system of those scalar fields is this one here. So now you have sum instead of integration. So these are variables, fields and canonical momenta, which are derivative with respect to velocities. Yeah. So I think that here should be dot. Yeah, derivative with respect to velocity gives you momentum, which in this case is just phi squared. The Hamiltonian is this one. So this is the usual field theory, but for many particles, and upon quantization, phi and pi satisfy the following, become the operators that satisfy this equal time commutation relations. In the continuous limit, the discrete index R becomes the continuous index sigma, and phi of R becomes phi of sigma. And the action is then this action here, where S sigma of sigma dot is equal to this delta function written in this way with indices. Now we can distinguish two cases. The first case is this simple case in which S is just this simple delta function, and this is the action for a continuous bunch of non-interacting fields. Second possibility is that S of sigma and sigma prime is an arbitrary metric. So can in principle be a general metric in the space of the fields phi. So this is metric, and this is its inverse. This index is up. You have the inverse metric, and multiplication of those metrics gives you delta function. Equation of motion are then this one, either for fields with index down or for fields with index up. The canonical and commutational relation are this one. The Hamiltonian is this one, and the field can be expanded in terms of creation and annihilation operators satisfying this relation here. Then the Hamiltonian is just this expression here. Momentum operator is given by this expression. I don't know if you are familiar with field theory, but those who are would recognize that this is well known in field theory. Momentum is given by this expression, which can be then written as this part plus 0 point energy. 0 point energy comes because you change the order of these operators, and then this half disappears, but what remains is infinite term, which causes problem in field theory. But in our case, it will cancel out. So let us now calculate the time derivative of the expectation value of the momentum operator. So this is expectation value. This is the state. And expectation value gives you then these things here. Sorry if I go quickly, but this well known. If H is Hamiltonian, this is commutator of Hamiltonian with momentum. Of course, if you, this is operator equation for P has this commutator, but expectation value has this sandwich between the states. So what is the state? The state here is given by this expression, which is in which creation operators are applied to vacuum, and G as function of P are wave packet profile, and here you have the product over all those possibilities here. So yeah, you have multi-particle analog of multi-particle state, because here you have this product. In discrete case, this would be just index R. Discrete index, but in continuous, it is written this way, with continuous index. Mathematicians say that this is not well defined, but okay, one can do conceptual and also exact calculation with this notation. Okay, now from this section, you arrive at this section. Now, why I considered omega dependent on position? Because if omega would not depend on position, then this derivative of expectation value would vanish. But for the moment, it is convenient that it does not vanish. Now I must find where we are. Yeah. So this is again the same expression of the previous slide. And so let us choose a metric in the space of the fields. So this S, sigma is the metric in the space of the field, which we choose to be this one. 1 plus lambda and this D'Alembert operator, dA in the space of the brane parameters. Now you can switch by performing partial integrations. This guy here can be moved to G. So you get this expression here, where omega P is here, is sigma dependent, and then you have these terms here with twice partial derivatives on the G, which, as I remind you, is wave packet profile. So this is the time derivative of the expectation value of the total momentum of the brane. We can omit integration over sigma, and then we have derivative of the momentum of the segment of the brane. This is this one. Now, by doing this, we can take omega constant and arrive at this expression and put omega, because omega is constant, we can take this one of those partial derivatives out of the integral. And this is then just like divergent of a certain current. Now, look, but this is now okay, saying that omega is constant, because the overall momentum of the brane, which is, if it is free, not interacting from the environment, is of course conserved. But the momentum of the part of the brane, or the segment of the brane, is not constant. Various parts of the brane can move relative to each other, and this is denoted by this expression here, or reflected in this expression here. Now, let us now Fourier transform this wave packet profile, where f is now Fourier transform this wave packet profile in coordinate space, and by taking for the wave packet profile this Gaussian-like wave packet. This can be done at initial time only because Gaussian wave packet spreads over time. But initially, we can say that this is Gaussian wave packet and insert it into this equation here, and then we arrive at this equation here. And this is very similar to the equation of motion for the Dirac, for the classical brane. But if we improve the metric, if we take this expression for the metric in the brane space, in which we insert also the determinant in the space of the parameters on the brane, then instead of this section, we obtain this section here, where this sigma, which was here the integral of the brane with this determinant, is approximately equal to this expression here. And the consequence is that we have now here this equation, but of course this determinant now again cancel, but now instead of this delta S, we have delta sigma. Now we can make correspondence with a classical Nambu-Goto brane, because this momentum here that we took expectation value corresponds to classical momentum. Classical momentum of the brane is this one, and we also make correspondence between this term here and this term here, and we arrive at this equation here, which at the beginning we had as the equation of motion of the Dirac-Nambu-Goto brane. Okay, I was playing with branes. Branes was considered as an object in multidimensional space, but the exercises with the brane space were just a tip of an iceberg, because instead of one brane, a configuration can consist of many branes or many point particles or both. So now such a generic, complicated, whatever configuration can be denoted by X capital M, and it is a function of certain parameter. And this M either means system of point particles, where this, what is this I? Yeah. I is the index that says which point particle, sigma is the index which says which point on the brane, and or if you have many branes, then you have also this index K, which has nothing to do with this K we had at the beginning. This is no index, which says which of the many branes. We also can sample a brane with this tensor coordinate, antisymmetric tensor coordinate, mapping from infinite dimension to finite dimension. One such possibility of sampling is to take just a center of mass. Then, instead of having a complicated description, you're interested only in the center of mass of the brane. But okay, like this. So here I have done a lot of work, but I will leave it. It would be too complicated. So the action for such a generic system is this one. And rho mn is a metric, and x dot m are velocities. Okay. We can consider configuration space C, now denoted C, as primary even in classical physics, and consider space-time as a subspace of configuration space. Look, here we have three different configurations, C1, C2, and C3. Yeah. Which differ only in the position of a single particle, this red dot here. So, and space-time is a subspace of this multidimensional space. So, in the configuration C1C2, the position of these particles is different, whereas the positions of all other particles are the same. In this picture, a four-dimensional space-time is just a subspace of configuration space associated with the degrees of freedom of a single particle. No, I have no. I will finish up. Here is a conclusion. Just let me summarize. So we have found that a brane can be considered as a point in a brane space M moving along a geodetic in M. The metric of M is not fixed. It is dynamical, like in general relativity. For a particular metric, we obtain the usual Nambu-Goto brane. More general metric give us interesting fancy branes that might be useful in scenario for quantum gravity in the presence of matter, and of course also in the Braneworld scenarios. The simplest is the case of flat metric that gives us flat branes. A flat brane can be straightforwardly quantized as a bunch of point particles. If we take a suitable interaction between the quantum fields, we obtain as an expectation value the classical Dirac-Nambu-Goto brane. We have thus found how to quantize branes via flat brane space. Non-flat branes are then objects of an effective classical theory that arises from the underlying quantum field theory of many interacting fields. The concept of configuration space is associated not only with branes, but with whatever physical system in classical and quantum theory. The concept of space time has to be revised by considering space-time as a subspace of the configuration space of the whole universe. So, look, we perceive this probe as moving in space-time through the universe. But space-time is in fact a subspace of the configuration space of the whole entire universe. Okay, here are some references, and so I have arrived at the end of my talk. So thank you very much for your attention.
Okay, thank you very much. I think we're going to open it up to questions now. If you want to, you can raise your hand. You can just unmute and jump in. We'll see what works best. Yeah, Jersey, go ahead.
Okay, good evening. Thank you very much for this very interesting talk and presentation. Very inspiring. I'm not very good in the manipulation you did, but some of them I met somewhere. And I have general question, because I saw that you perform frequently integration in infinite dimensional spaces. So do you find some difficulties with these procedures? I mean, existence of some measures in such spaces and so on and so on.
Usually people say that if they have double partial derivative in infinite dimension, they get delta function. But of course they get delta function if they consider a wrong metric. But if you consider more general metric, then this disappears. In my book, The Landscape of Theoretical Physics, I can do manipulation in infinite dimensional space and so on without problems. And also in the book by Hartfield on quantum, like this quantum field theory of point particles and strings, there is a chapter on functional calculus, and they can perfectly do a field theory with functionals. The states are functionals of fields and so on.
So there is not a big problem with measures on infinite dimensional spaces, yes?
Yeah, there could be a problem, yeah. But if you perform, you can get rid of measure by doing, by deriving equations of motion, even if measure is infinite. Oh, yes, you are right. Yeah, of course, you must then choose the set of, the subspace of infinite dimensional space, in order to define the measure. Yeah, you are right. Yeah, of course, there are technical problems when you wish to do actual calculations, but in the case that I'm considering here to derive equation of motion and so on, the problems with measure then can be avoided. Yeah.
Also, if I may have another question.
Yes.
If we didn't know the point particles equations and quantization of them, do you find, because your equation you presented us are very similar to quantum field theory expression in some extent. So my question is whether without knowing this quantum field theory part, do we really recover these equations? So imagine that we don't know quantum field theory for point particles. And do we really find these equations? Or other part of this question, whether these equations are uniquely derived from your setup? Up to which extent they are uniquely derived? Or they come from some approximation, some supposition?
Yeah, I don't know, because I know quantum field theory, so of course I was able to extend it to the case of a set of fields or infinite set of fields, and so I don't find problems. I'm sorry. Because with the equation that I wrote, you can manipulate as I did. I don't know. But do you wish that I find some transparency, some slide that you will point something?
No, I'm not saying that something is wrong in your presentation. Not at all.
No, I understood that you're not saying, but that how difficult it would be to derive without knowledge of quantum field theory. Yeah, of course, something you must know if you wish to do physics. Yeah.
Okay.
You cannot invent everything. Knowing quantum field theory, I envisage how to generalize it to the system of first non-interacting fields and then interacting fields. But what is interesting is that because this choice of metric in the space of field gives very interesting things if you elaborate further. This was done in this paper. Which one? In this paper here. Yeah. I don't know if you see the cursor. Do you see cursor? Yeah. No, you don't see cursor. Okay. So in the first one, quoted here in references, it's very interesting what happens. Yeah, it's not just whatever choice. It gives very interesting equation. In fact, instead of partial differential equation, partial functional, you get partial differential equation, and so on and so on. Maybe if you look in this paper, you will get some ideas concerning your question.
Yeah, thank you.
Okay, thank you.
Yeah, Bassam, go ahead.
Thank you for a very interesting talk. I have a question relating to, you mentioned somewhere the wave function, the wave packet.
Could you speak louder, please? Louder.
Yes.
Be
Thank you
closer to microphone.
Okay, thank you for a very interesting talk. You mentioned somewhere you derived a wave packet. So
Yes.
physically, what does this wave packet signify? What does it stand for?
Yeah, look here, of course, a lot of other work is behind. It touches to the problem of particle localization in relativistic theory and so on. Yeah. These are wave packets, yes, in quantum field theory. There are several schools. Majority says that you can't have consistent wave packets, but some people say that you can have. For instance, I think that it was Fleming, that particle position refers to certain inertial system, to certain, they say, space-time hypersurface. So these are indeed wave packets for time particles. Yes, you have wave packets. You have wave packet in momentum space. It is okay. Everybody says this is okay. But if you Fourier transform, people usually say in the old textbooks that this is problematic because Lorentz covariance is and so on. There are many problems, I think. But I have shown in the papers, and also Larry Horowitz has shown that there are no problems. And in my book, in this book, Stumbling Blocks Against Unification, there is a whole chapter, I think it is entitled Position or something like that in quantum field theory. This book is very expensive, but there is review articles on the subject. You will find it somewhere. I did not list it here. But okay, in this book, I reviewed this in great detail. Why one can nevertheless consider not only momentum, but also position space wave packets. Yeah, sorry if this goes outside what is usually taken for granted in physics, theoretical physics.
Thank you.
But there are many things that must be put together, rethought, revised, or how to say, yeah, to change, to go a little outside of the current knowledge. So, thank you.
Yeah, thank you so much for a great talk. I think that a couple of the questions kind of asked, how do we interpret, if we're describing things in brain space, then how do we interpret various features of brain space? Something that I was kind of curious about, and I have to admit I have a personal bias here, is I'm curious about whether we can use this notion of brain space to develop some sort of calculation of entropy for a brain, if we can have use the metric of brain space to describe
that entropy.
Yeah. Right.
Yeah, I think that it can be, of course, it can be done. Yeah. But of course, one must be careful. What is entropy? How is entropy defined? Because I don't know if you know a very interesting paper by Tribus in 71 in Scientific American, where he explained the concept of entropy very clearly, information and entropy and the relation between those two, and so on. Yeah. because if you have entropy is, according to that paper, is a measure of uncertainty of certain question. And question can be, what are position of particles in phase space? And if particle position are ordered, then you have some information. And of course, then entropy is low. But when this is mixed, you lose information, and then entropy is low. And the difference between those two entropies and uncertainties of the knowledge concerning a certain question is information. And there is Tribus said that there is direct relation between entropy in physics and entropy in information theory. Just you put this Boltzmann constant in between, and you have translation of these two concepts.
Okay, if there are any other questions, you can raise a hand or unmute. If not, I think we can thank our speaker again. Matej, thank you so much.
Okay, thank you very much
for a very interesting talk.
For being with me and having passion to follow or try to follow these complicated derivations. Thank you.
Thank you so much.
Thank you.